Good morning.
Good morning. How's everybody doing today? Let me finish. Just waiting on a few more people. Okay. All right. I guess nobody else is joining us, so let's share. We shall be completing promptly the second part of the review today. So I'm going down there. Okay. Yeah, here we go. Okay. We're going to share now. We've already done one of these. We are not going to go to, yeah, this one, right? This is where we stop. Okay, for this one, you'll need a periodic table. And here we go. We have, okay, potassium. Okay, remember, whenever you see this kind of symbol, the top number is always this number, the mass number right here, okay? The atomic number you look for in the periodic table, and it happens to be 19, which is always the same as this number, always. And then the protons here, neutrons, if you subtract it from the mass number, you get the neutrons. And the electrons is the same as the protons unless you have a positive or a negative. If you have a positive, then you subtract. Okay. Let me write that down up there because that'll help you look at that the way it's supposed to be. Okay. So right, those two are the same. Okay, somebody just hold on. Somebody just answered. Okay. And let me. Okay. Okay. All right. So like I was saying, those two are the same. Now this one minus this one equals that one. You see what I'm doing here? So this right here, right, equals that. And then this is, this one I would say if positive, subtract, if negative, add, right? Okay, so that's just for you to have an idea. All right, calcium, once again, it's giving us that. So we need to write down 41 right there. Then look in the periodic table and see that calcium is number 20. Excuse me. The protons are 20 also. Remember, those two are the same. The neutrons, we subtract those two. It's going to be 21. And then the electrons, it's also going to be 20 because they are the same as the electron, as the protons, because we have no charge. Okay. The next one, oh, sorry, we start with 69 because we already have that. The next part is, where is gallium? Hello, gallium. 31, okay. So 31 goes here too. Then we subtract those two, we get 38. And then with the +3, we're subtracting from 31. So we're going to get 28, right? This one is 37 right here. The atomic number for chlorine is 17. That means the protons are 17. The neutrons is 20, right? And the electrons is going to be 18 because it's negative. You see that? So if negative, add. This one, oops, this one right here is 18, right? Number 4 oxygen is 8. Protons, 8. Neutrons obviously going to be 10. And then the electrons is going to be 8 again because there's no positive or negative. They just, and then uranium, notice it says 235. And uranium's number is 92. Okay, so 92 here. Now we subtract. Let's see what that is. Let's see. 3 here. Hold on. Oh, I'm doing that in my head. 13 minus 9 is 4. So 143. Okay. Okay. The electrons is going to be, well, you have 92 normally. So when you subtract 4 from 92, you get 88, right? And that's that. Okay, you see? So that's how you fill that out. That's weird. All right. So the next one is asking us, okay, so let me clear that. Okay. This next one is asking us to calculate silver, the mass of silver. Okay. So remember for this one, what you do is you take the atomic number, multiply it times the percentage, not in percent. So you got to divide 51.8 into 100, and that'll give you 0.518, right? And then add it to the next one, which is 109, right? Times the same thing, so 0.482. Close it, and then equals. Okay, we shall see. Oh, I'll be right back. I left my calculator, or actually my phone, which is my calculator, in the room. I'll be back. I'll go get it. Okay. Here I got it. Sorry about that. I just totally forgot to grab it. All right. And like I said, I use my calculator. Right now it's my phone, so I have to have that. So 107 times 0.518 plus 109 times 482.42. Okay. And I get, man, that's supposed to be equal. Oops, it's supposed to be equal. Equals 107 point, it says to 3 decimal places, so 964. And that is it right there. Okay. And that's how you do it. That's just an example. Okay. What are the long and short electron configurations for the following? All right, I'm gonna do the long for 2 of them and the short for 2 of them, and then also do the orbital configurations for each of those 2. I'm gonna do one that's an atom and one that's an ion. That way you'll remember how to do both of those. And that's it. Okay, so I'm gonna do phosphorus. Okay, and I'm gonna do fluorine for you. No, sorry, sulfur for you. Okay, those are the 2 that I'm gonna do for you. All right, so for phosphorus, the long form, so you have to grab your periodic table for that one. The long form is 1s2 that's a 6. That's 6 in that one I do. Okay, but you can see it better now. 2p6, 3s2. That's the long, right? And 3p3. Okay. That is your first one. That is phosphorus. That's the long form. The short form, remember you take the first element, which is neon, right? And you use that one, first noble gas. And then you just use 3s2, 3p3. The last thing is to do the orbital configuration. For that, you have to write it. Let me see where I'm going to write it, because I guess up here. Okay, for this one, this is your 1s, right? Your 2s. Your 2p is these. This is your 3s, and this is your 3p. Okay, so remember, you have to put in your arrows. First, going one way, right? Then going the other way. This one's, oops, this one's full. So it's this one, so you just, oops. Yeah, it's an ugly. Okay, there we go. And then this one, you have 3. 1, 2, 3, and that's it. There's your electron configuration for that one. So electron configuration long, electron configuration short, and orbital diagram for phosphorus. Okay. Now let me clear that and do the one for sulfur. But sulfur itself, okay, sulfur itself would be 1s2, 2s2, 2, looking for sulfur, yeah, 6, 3s2, and 3p4. That would be sulfur itself, right? Sulfur with a -2 means you have 2 extra, right? So it's going to be 1s2, 2s2, 2p6, 3s2, and 3p. And I'm going to make this one in a different color just to make a point that that's what's changing, right? Because you're going to add 2 to it, and those 2 are going to be there. Now the short configuration, I'm just going to write directly over this stuff. I think you can see it enough, well enough. So the shortcut, right, is going to be your neon again. And you just bring that down this 3s2 and 3p6. I'm moving, definitely changing that 6 to blue just so that you see that it's just the only reason it's like that. It's because of that. Okay. Next thing is our electron configuration, orbital diagram, which I'm going to draw up here again. Okay, so this is your 1s, 2s, this is your 2p, right? This is your 3s, and this one is your 3p. Okay, so here you have 1s, 2s, 3s, 2p is full, so 3s is also full. The 3p is also full, but normally that right there would be sulfur. We are going to add 2 more electrons that came from somewhere else. You see that? So I'm just doing the drawing like that so that you see that those electrons actually are not part of the atom itself. And that's why you have the -2, right? And that's where these are in blue right here also. Just so that you see that you had an extra 2 added to them. All right, that's that one. Now, here it says name at least one trend among each of the periodic families. Well, I would, this is just my own suggestion, is that for hold on, I'm gonna type it in. For each one of them, I'm gonna use, for alkali metals, I'm gonna use atomic radius, and you can use whichever one you want. But remember, we're talking about for each of the families. So for the alkali metals, the atomic radius increases, right? As you go down the period. Sorry, the family, the group. The down. Oh Lord, I can't type today. Down, the. My fingers were moved. Okay. All right. For alkaline earth metals, I'm going to use electron affinity just because I can. Okay. And in this case, it decreases or it increases. You're going to say increases as you go up, right? Group. They're all going to be, I'm going to do all increases because it's just easier if you're constant. The halogens, I'm going to do, oh, you know what? Let's not do electron affinity. Let's do ionization energy here. It's still the same, but you'll see why I'm not. Okay, there we go. Okay, for the halogens, I'm going to use electronegativity. Electronegativity. There we go. Increases as you go up the group. And now the noble gases. The reason I wanted to leave electron affinity for the noble gases is because it's really the only one that they're included in. So increases as you go up. Okay. All right. So you could also add here as a side note, it increases as you go. And this is just me adding this. As you go to the left, right? Where is it? As you go left on the A period. Right. That's that one because it does increase as you go left. And then this one, this is just a side note because I wanted you to remember that. Okay, or across a period, whatever. I don't care what you want to call it, but I'm going to copy this because it's the same for all of them after that. It makes life easier, doesn't it? Okay. So there you go. Those are your trends. Okay. The next one says if a noble gas could form a positive 1 ion, which one would form it most easily? So basically this has to deal with electron affinity. In order to form one ion, it would have to let go of the ions. So it can't be helium, right? So it has to be the lowest. And the answer to that would be radon. Right? Because it would have the most electrons. Okay. How does an ionic bond differ from a covalent bond? Ionic bonds not share, but what do you call it? Transfer. Yeah. Transfer electrons from metal to non-metal. While covalent bonds share electrons between two non-metals. What's that? Okay. Now, how would we know if these are ionic or covalent? Okay. First of all, let's do the ionic and covalent thing. And let's do red for the, we're going to color code things. Okay. So, ionic we're going to do in blue. Okay. So ionic is gonna be blue. I said blue, it's red. Sorry, red. How do we know? Well, we have to have a metal and a non-metal. Okay. Where else do we have a metal and a non-metal? Right here, right? Are those the only ones? Yes. Now, the next thing is to do the non-polar. Okay. Non-polar, you would have to actually grab your ionization energies that I gave you, well, that I asked you to print. Hold on, I have them here. Find them. Ionization energy. I have a bunch of stuff on my. See them. I have them. I'm just not seeing them in here. See everything but that. Hold on. And so far, not good. Ionization energies are usually in here. I do not see them at all. They are not in here. So where did you guys go? Nope, that's not it either. Nope, that's not it either. Okay, well, ionization energies, I can show you where to go get them. I'm gonna go get them myself because I can't find them here. And I normally have them. But in order to do that, what you need to do is you need to go to back to your okay. And from here we gotta go to hold on. Where are you? Periodicity. That's what I want is a periodicity PowerPoint. I think I passed it. Oh, not yet. I didn't. Okay. Should be right around here somewhere. Vesper. Okay, here we go. All right. And trends. We need the trends. Why am I not seeing you? I just missed it. Balancing equations. I missed it because it's got to be right here. Periodicity. Oh, it's right above that. There it is. No, that's not it either. Darn it. I know it's here somewhere. Did I like totally miss it? There it is. Boy, I did. All right, so you have to go here and we're just gonna have it. We gotta go there and you gotta go to this particular slide right here. Not quite there. This one. This is the one we need. Okay, I'm gonna print this. So we'll have it on the side. And I just need to this one slide. So just, slide Slide number are you? 43? Okay, I should have done it, but said it was slide 43, so let's hope. Yeah, there it is. Print it, and we'll just call it electronegativity. Okay, save it, and that way we'll have it. All right, now, hopefully that did it. And we can get it. All right, so our electronegativity chart, we just need to come look for it here. Come on, quick access. Come on. Oh, I hate when that happens. This PC. Here we go. Now I need quick access. That should be there. It's not there. Great. I just gave it a name and everything. Ah, there it is. I knew it had to be there. Okay. So we're gonna just bring it up, and that way we can be switching between them because we need it. Go away. All right. So we're going to be, like I said, switching between them. You see how you've got all these numbers on here? Well, we need those numbers. So we're going to minimize it. And we're going to be looking for the numbers for hydrogen, for example, is 2.1 and oxygen is 3.5. Did you see that? Okay. So in order to do that, you've got the 3.5 from the hydrogen, which I said I was going to do. Okay, so you got 3.5 and 2.1, right? Which gives you a difference of 1.4. So this one is going to be polar covalent, and this moved, hold on, this moved too much. It's supposed to be ionic bond here, but it didn't work. There we go. Okay, so polar covalent is going to be in green. There we go. All right, the next one we have is nitrogen and oxygen. So we know oxygen is 3.5. What is nitrogen? Well, let's go check, right? We'll go check on our next one. Oh, we need a mouse. Okay. Nitrogen is 3. You see that? Okay. And based on that, 3 minus 3.5 minus 3, oops, sorry. And we're going to make that blue. I said blue, come here you. Okay, draw. Okay, so 3.5 minus 3. This one could be either. It's going to be 0.5. So we think for now that that's going to be non-polar covalent. Okay. Carbon and sulfur should be non-polar covalent, and so should be that one. But we'll see. We'll see. All right. So the next thing to do is go check the electronegativities for these other two. All right. So for those two, we need carbon and sulfur. I need my mouse. That's why I can't get it. Okay, carbon and sulfur. Carbon is 2.5, sulfur is 2.5. See, that's a 0. So that actually tells you that's electronegativity. Is So carbon and sulfur, that's 2.5 minus 2.5, right? We just saw that. So that right there shows you that this is correct. And then boron and fluorine should be nonpolar also, but we shall go check. Based on this, will it give us the right answer? Well, we don't know. That's why we check first. Oh, where's my periodicity? Okay, so fluorine is 4, boron is 2. This is very polar, doesn't it? Based on that, it is. Okay, so let's go find out. Officially, is it or not? Well, okay. So boron, we said was, I know I need to bring back the the other one. Where did you go? There you are. This is the one I need. Okay. Boron was 2 and fluorine is 4. So that sounds like it's very polar based on that, right? So according to our results here, it seems very polar. Now, boron happens to be a non-metal. I mean, not a non-metal, sorry, a metalloid. So it's very possible that we're getting misled because of that. So the one thing to do is when we're not sure, and we need to do this one because this one's close to being a possibility. This one's definitely nonpolar, but these two, we need to do the, the atomic, the molecular shape for them. So in order to do that, do you remember that you need to take your nitrogen, which is in group 5, right? Hold on, let me grab my periodic table. I need to do this one. Okay. So nitrogen in group 5 gives you 5 electrons. Remember how to do that? The little structure? Yeah. Okay. So that would be your first thing you need to do. And then you have 2 oxygens in group 6, so that's 12. Plus, there is no charge on that one, is there? But it should be an O2 negative, so you add 1. So you add these and you get 18. Okay, so if you put NO2, remember how to do that? We subtract 4 from there. You got 14 left. Okay, 14 would be enough for the oxygen, but we need 1 extra bond, so we need a double bond. And we have this, 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 this. We have 1 here. We have dots here, dots here. Oops. You know what? I forgot my dots. I'm gonna undo those dots because they're horrible. Undo the dots. Come on. Undo my dots. There we go. I'm gonna use my dots like I normally do them. Okay, so here, 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 and there. So this is polar. You see that? So now we can officially say that this is actually a polar. See, I'm circling it in green now because it is a polar, because we have that. Now BF3, which we said was nonpolar, because, we just thought it would be. Why did we think it would be? We didn't know. We just thought it would be. Why? I knew why. But it's because boron is a, oh, come on, give me my color. Boron You got trifluoride, right? See, boron is an exception, so it doesn't have an extra lone pair. So boron is nonpolar, even though the difference is so much. So you cannot always rely on this, okay? Because this is a metalloid. Metalloids are not your normal people, you know? Boron is a metalloid, and that is a problem. That's a metalloid and a non-metal. So normally, covalent bonds come from a metal non-metal kind of thing. So even though this is named as a covalent, right? Even though it's named as a covalent because it's boron trifluoride, it actually is more ionic because you have boron acting as a metal transferring the electrons, but they're actually sharing them, which is almost a transfer because they're so different. All right, clear that, and there's your answers. Okay, now, why does a certain covalent compound have a distinct odor while a certain ionic compound has no detectable aroma? Well, this leads to the one property of covalent compounds and ionic compounds that are different from each other. And one of them is, you can say, because the covalent compound has a lower boiling point than the ion. And that is how it is. Covalent compounds have lower boiling points than ionic compounds, okay? And that's why you can smell alcohol so quickly. Alcohol is covalent, but you cannot smell salt necessarily, right? You don't, because it is an ionic. All right. How many valence electrons are there in these? Okay. What you have to do, remember, is look at your periodic table. When you look at your periodic table, for silicon, you would have 4. I am just going to write them down with my finger over here in red. All right, so 4 on that one. Potassium really only has 1, but potassium plus 1 has actually 8, right? Neon has 8. Oxygen 2 negative normally has 6, but you add 2 and it has 8. Hydrogen negative 1, that means you have added 1, so it's 2. And nitrogen normally has 5. See that? And now the question is, why are some solvents polar and some non-polar? Which would you use to dissolve salt? Okay. So the question here is very simple. Let's see. Polar solvents have a dipole solvents, which results in a partial charge. Oh, 2 L's. Partial charge. Okay. For each atom. Okay. All right. Now, salt is an ionic compound, and it dissociates in water in solvent, in polar solvents. Okay. Because it is attracted to the partial. No, its ions, I should say. I should say its ions are attracted. That makes it much better. To the partial charges in the covalent polar covalent compound. There we go. There we go. That would be my answer to that one. Okay. So basically, when you have water, remember you have an oxygen, and you have a hydrogen, and you have another hydrogen, and then you have, oops, let me do my dots with these, right? So very polar. So along comes sodium chloride, and the dipole obviously is coming into this way, right? Which means this is going to be your negative, and these are going to be your positives, right? Well, sodium chloride comes along, and sodium is going to be your positive, right? So sodium comes here, and your chlorine comes here. See? So it's going to be attracted that way. And that's why a polar solvent with its partial positives and partial negatives is going to attract an ionic compound, because ionic compounds will dissociate. Okay. All right, clear. All right. Next. Okay, what do we have next? Draw the electron dot structures for each one of those. This is like the easiest thing in the world to do. All you have to do is redraw. Let me do that in blue. Redraw your elements, right? Look up which period they're in, which group they're in, sorry. And the group number tells you how many dots. Okay, this is in group 4, so you go 1, 2, 3, 4. I know, right? Helium happens to be in group 1, and they are paired because it's the 1s2. This is full. Phosphorus is in group 5, so you go 1, 2, 3, 4, 5. Nitrogen is also in group 5, right? 1, 2, 3, 4, 5. Aluminum is in group 3, 1, 2, 3. And sulfur is in group 6, 1, 2, 3, 4, 5. Sorry, that is not a very good one. 5, 6. There you go. So simple. I told you. Super easy. All right. Now comes the harder part, the naming. It's been a while since you guys had to do this. Oops. Sorry. I'm going to bring this up, but I need some room, so I'm going to leave it like that. And on these, I'm only going to do every other again. So I'm going to circle the ones that I'm going to do. I'm going to do A. Oops. But I stamp them. I'll stamp them instead. I'm going to do A, C, E, G, I. You get the point, right? K, M, O, and Q. Okay. So for A, the name is chlorine tetroxide. very obviously with the tetra here, right? Oops, let me get the, undo that one and do the draw. Okay. Okay, for that one, okay, the tetroxide, that tells me it's a covalent compound. Plus, you can look at it and see that you have chlorine and you have oxygen. And for that, you're going to have that. And that's it, ClO4. It's telling you what to write. It says chlorine and 4 oxygens. Now, the next one's not so easy. This one is a polyatomic ion. It tells us iron 3. And then it tells us it's hydroxide, right? So when we cross, we get iron, that gets 1, and the OH gets to 3. See? The next one after that, we're going to do is an acid. Hydro tells me this is the binary. So that means you have a hydrogen and a bromine. When you cross them, obviously it's just HBr. But in order for this to be the acid, remember, it has to be in aqueous form. Don't forget that part because it is very important. Otherwise, it's just hydrogen bromide. Oops. All right. So that's those 3 right there. The next one that we have is sulfurous acid, right? Sulfurous acid, once again, is telling me acid, but you notice there's no hydro. So that means this hydrogen, and you have sulfite, because sulfurous is talking about sulfite, not sulfate, but sulfite. So when you cross, you get H2SO3. And this one doesn't have to be aqueous or anything because it is a ternary acid or an oxy acid. All right, the next one, phosphoric acid, okay, phosphate. See, phosphoric, ic comes from 8, OUS comes from ite. So just remember, I ate and I got the hiccups. That way you remember 8, ic. All right, H plus, and phosphate is PO4 negative 3. Crossing gives you H3PO4. And that's your acid. And then the next one that we have is tungsten 5 bromide. You notice how it's telling us tungsten 5 bromide. Okay, crossing gives me tungsten with 1 and bromine with 5. And there you go. All right, I'm gonna have to erase these to finish because we ran out of room. All right, now we said we were gonna do mercury nitrate and sulfuric acid. Okay, so mercury 1 nitrate. Mercury 1 is Hg plus, right? Nitrate is NO3 and it's negative. So crossing, you do not have a difference. It's just HgNO3. The next one after that is sulfuric acid. So ic comes from 8. Remember that? So sulfuric means that you have the sulfate. Crossing is H2SO4. Sorry, throat's dry. Okay, there we go. I feel better now. I always get a dry throat when I talk a lot. Okay, so here we go. Next one. The last one that we said we were going to do is Q, which is molybdenum 6 iodide. Molybdenum. Oops, that's an ugly one. Okay, undo. Molybdenum 6 iodide. There you go. And don't forget ammonia. It's always NH3. It's just the name for it. Okay, so that's one of those you have to remember yourself. All right, that's those. All right, now we have to clear these. And we are going to go to the next part where we do the opposite. We write the name for them. This should be easier, but I'm still going to leave all of that room up there because sometimes we have these elements that are more of and transition elements and things like that. All right, so I'm going to stamp the ones that we're going to use, and they're going to be the same. A, C, so A, C, E, E. So actually, it's this whole, just these two, right? I'm going to skip all the others. Okay, so cobalt. Cobalt happens to be a transition metal. So in order to give it a name, you have to decompose your formula. Okay, you know that fluorine is a negative, right? And there are 3 of them. So 3 times 1 is 3. So in order for this to be a 0, right, that has to be the cobalt 3. So now you can name it, okay? Now you can see that this is cobalt 3 fluoride. And it's fluoride, not fluorate or anything like that, because it's a single element, right? So ide. Okay. The next one is KMNO4. So K, that is potassium. This is easy because K is potassium, and potassium is not a transition metal. And MnO4, if you look at your polyatomic ion sheet, it is permanganate. But let me make sure. Make sure I'm right. I do believe it's permanganate. Right here. Okay. It is potassium. KMNO4. It is permanganate. So that is the name. Potassium permanganate. Remember, all names are the names of the ions, right? Put together. So when you see potassium, see, and then MnO4 is permanganate. Simple enough to do. Just got to make sure that you do it right. Okay, let's clear that. Oops, let's not clear all of it because then I will have, let's just erase instead. Takes longer, but well, okay. So the next one that we have is HNO3. H indicates acid. NO3 is nitrate. Remember nitrate? So nitric, right? So the answer for that one is nitric acid. That's this one, right? We've done this one, this one. Now I got this one. Well, lithium is not a transition metal either, and OH is hydroxide. Oops, not that close. There we go. It's 2 words. Oh, it's easy. All right, now we're gonna do this one. I know, right? Okay, so looking at it, we can kind of see that we have the copper ion and the nitrate ion, but we do not know which copper until we look at what's here. 2 times 1 is 2, so that must be the 2 plus, right? So now we can name it copper 2 nitrate, and you notice there's 6 waters, so that would be hexa for the 6 and hydrate for the waters. Okay, so copper 2 nitrate hexahydrate. I know that's a long name. Okay, let me clear these again. Okay, so whenever we're naming stuff, we got to make sure we got the right ions. That's really the takeaway on this one. All right, the next one that we have is N2S5. N happens to be a non-metal, so it's sulfur, nitrogen and sulfur. So N has 2, so that would be nitrogen, and how many sulfurs? So it's penta, right? Sulfide. And this is what is known as a covalent compound, dipenta. See? Dinitrogen pentasulfide. That's what it's saying. Okay. The next one is VO5, V2O5. Okay, for this one, we have to figure out what vanadium is. We know that oxygen is always negative. And this is a 2, right? Okay. So 5 times 2 is 10, divided by 2 is 5. So this has to be the positive 5. You see that? So then the name is vanadium 5 oxide. Oxide, because it's just oxygen. Okay. And then the next one, where are you? Oh, H3PO4. Okay, let me erase these. H3PO4 is an acid. How do we know? It starts with H, right? And PO4 happens to be phosphate. And phosphate, not phosphide, right? Phosphate. So H3PO4, the name is phosphoric acid because you have phosphate and it came from phosphate. So phosphoric acid, and that's it. That's this one right here, right? We've done those 2. Right, the next one that we have is CS2. That one's easy. Remember, we never used the mono. We just say carbon. And next is di, because we have 2 sulfurs. So sulfide, that is a covalent compound. That's that one. And the last one we have is tantalum. And we do not know which tantalum we have until we decompose it. And you notice it's 3 negative, right? Because chlorine is 3 negative. So 3 times 1, So it's positive 3. So his name is tantalum 3. And I because it's just 1. Okay. And that's that. That's how you know who's who. All right. I've done all of those. So let me clear that. And we will, let me see what else we got. Okay. This is too long. There is no way we can do this one right now. Just review your, you know, review your entire thing and do, your how to make the Lewis structure, that kind of thing. And the next time we will do those. And we will balance the chemical equations. We do mole conversions and percent composition. And that'll be the end of our review. And you can always ask me questions. And once you do, if you do something and you don't understand it, you ask me. And that'll be it. We will be done. You'll be ready to take your final, which is found on Connect. All right. And that is it. So you ladies have a wonderful rest of your Tuesday. Where am I going? Wednesday. And I'll see you next Monday. Take care.